Hello and welcome back to the channel. In this video, we will be learning to build a speech to text model from scratch. We are going to input an audio waveform, apply some deep learning, and output the transcription of what was spoken in the video. Along the way, I will be showing you some alternative methods and the pros and cons of each approach, and hopefully you're gonna have a lot of fun learning it. And without further delays, let's get on with it. Alright, so we are going to be using this dataset, which is a subset of the larger Timeit or Timeit dataset, which I found in Hugging Face. It has around 1600 examples. It's quite a short dataset, but the goal of this tutorial is to teach, is to educate, is to show some Pytorch. So hopefully even this small dataset is going to get the job done. All right, so let's have a look at how this data set actually looks like. So first we are gonna load the data set. Obviously, if you're running this code for the first time, it's going to actually download that data set first and then you'll be able to load it. But I've downloaded it before, so it didn't take any time for me. So if you look at how the data set looks like, it basically contains two keys. One is the audio, which contains an array, and we're going to have a look at what this array is, and something called the sampling rate. And it also has a transcription. This is the text that was said in this audio. So if we did some more printing, we will see that the audio has 35,840 values. The length of the audio is 2.24 seconds. And the sample rate, as we had already seen here, is 16,000. Now, what is a sample rate? Audio is just a sequence of amplitude values across time. A sampling rate basically means how many amplitudes were captured for 1 second of audio. This being 16,000 means that there are 16,000 float values to represent 1 second of audio. So it runs from 0 to the end of the time, and this is the waveform that defining this audio. So let's say you zoom in between 0 to say 100 milliseconds. This is how 100 millisecond of the audio looks like, which contains about 1600 values instead of 16,000. And obviously if you zoom in even further, let's say 10 milliseconds, this is how the amplitude values look like for the first 10 millisecond of this audio. And so let's see what the audio plays like. So if I play the audio,
Don't ask me to carry an oily rag like that.
so it says, don't ask me to carry an oily rag like that. Okay, that seems like a solid start. We have some audio, we have some text to go along with it. We know how the data is represented. Now, all we need to do is to learn a model, some sort of a machine learning model, some sort of a deep learning model that transfers the data from this format. Let's go print it back in the way it used to be. Let's say whatever. So we have this audio waveform and we want to learn from these amplitude values into the text transcription right there. Basically, neural networks don't really understand text out of the box. They understand bytes, they understand characters, they understand categorical variables. So we somehow need to tokenize the text so that we can make neural networks see them as discretized values. There are a lot of ways you can tokenize text. We're going to opt for a simple character tokenizer method. Basically, here you have every alphabet that you're ever going to need, A to Z, and also some additional characters that I'm going to get to in a minute. The advantage of having a character tokenization is that you don't need to worry about out of vocabulary tokens any longer. So if your audio says something completely random that was not part of your subword or word vocabulary file, like azublablam, you cannot really predict azublablam from a simple word based vocabulary. You can still predict with a subword tokenizer, but with a character tokenizer, you can output any word that you want. Additionally, the input length is very different from the output length. The output sequence is always going to be shorter than the input sequence, because as you can clearly see, the audio input has 16,000 values per second. But even if you do a character encoding, you can say like 2 or 3 letters per second. So obviously, if you wanted to train a simple transformer model that inputs the audio in one end and outputs the text at the other end, the sequence lengths of the audio and the text are going to be different. And more concretely, the output text is going to have a lot of blank spaces. And for this reason, our character tokenizer will also have a special blank token. Now, how this blank token is used during the loss calculation, we're going to get to a little bit later in the video. If you're curious, we're going to use something called as a CTC loss to train this transcription model. But that's kind of getting ahead of ourselves. Let's come back and think about the character tokenizer a little longer. So you have the 26 alphabets. You have this special blank token that you're going to use to address the fact that your target text sequence is going to be a lot shorter than your input audio sequence. And we are going to add 2 more tokens. One, a space token, which represent when there is a boundary between words, and we'll also incorporate an apostrophe token, which will be used to predict apostrophe s or apostrophe re and everything like that. So to create this tokenizer, you just basically add this list of tokens, and this box thing is basically our blank token that we spoke about. And you add all of the alphabets, and you add the space, which stands for the word boundary, and finally you add this apostrophe to account for all of those apostrophe s stuff that we spoke about. And that's basically it. That's how you create a tokenizer. Let's just copy this entire thing and see how the tokenizer sort of looks like in our notebook. Let's see how the vocab looks like. Yep, you can see that it has all of the alphabets, and every alphabet has an associated integer value. Let's sort this guy so that you can see it more properly. Let's say sorted. Uh, yes, like that. And yeah, as you can see that you have all of the characters here. And if you were to, let's say, tokenize this guy, well, first of all, we have to make it into an uppercase string, because our tokenizer has only uppercase strings. And then we are going to do input IZs tokenizer.encode transcript, and this is going to give us our transcript. Let's see IDs. And here you can see that this is basically tokenized our input text, which was don't ask me to carry an oily rag like that, into this string. And you can see that the first letter is D, which has been transferred to 4 because D is the 4th letter in the alphabet. And then the next letter is O, which has been mapped to 15, and O is definitely the 15th one. And the space comes after DON, so 14. So this is 27, and 27 is the space. The point of this entire exercise is that we now got our input waveforms, which is basically a sequence of amplitude values, and we have got the output sequence, which looks like a string of tokens, like an array of tokens, which are all categorical in nature. And we have a way to encode and decode back and forth between its text representation and its integer representation. So now that we have one x and y, meaning one input output pair, we can now write a simple data loader function which basically collates all of that information and returns it in a batch. To do that, this dataset.py file just has this collect function and this get tokenizer function, which we already saw, and this get item function, which extracts one example from the dataset, which contains the audio array, which is converted into a tensor. and it contains the text, which is converted to the uppercase and then tokenized with the self tokenizer encode thing, and then the rest of it just takes care of itself. I've written a simple helper function which takes in a batch size, number of examples, just says if you want to train on a smaller subset of the original dataset, and some other processing stuff to basically create the dataset. Let's quickly look at what this thing looks like. Let's say the audio is that, and then you have the input IDs, which are this, and let's print those shapes. And let's also do a breakpoint here to show what they look like. All right, so you can see that the batch size is 32, and you have the audio, which is of that shape, and you got again the text is 32 and 78. So if I just show you what the input IDs is going to look like, let's print the first four. You can see these are the sequence of these numbers, and in an audio, basically, I'm not going to print this. Okay, I'm just going to print this. Okay, it's truncated, but as you can see that the shape is pretty high. Now in the next section, we're going to start looking at how to process these information and learn a model that can transfer this into this. So at this stage, it might be worth mentioning some of the different approaches to audio transcription. First, you can decide if you want to train in the waveform space or you want to train in the frequency space. A lot of earlier deep learning method used something called as the MFCC to model the speech. Basically, given the speech waveforms, you do some Fourier transforms to convert your original waveform into the frequency domain, and then you extract the frequencies that are most perceptible by humans. And doing this, you end up with a very compact representation of your audio, and then you can use machine learning on top of this. But modern deep learning methods almost never consider MFCC as the go-to method. The reason is it loses a lot of information and it becomes difficult to train large-scale text transcription models. So a lot of modern deep learning methods just learn directly from the audio, and that's what we're also going to do. So in the question of waveform versus frequency, we're going to go with waveform. The second option is what kind of architecture are we talking about? Well, there are two main ways you can think about it. The first is an encoder-decoder architecture. If you are familiar with sequence to sequence tasks like language translation, for example, you might know about what encoder decoder architectures are. Basically, you have an input sequence which you process through some sequence model like a transformer or a GRU or an RNN, and then you encode it into a latent representation. And from this latent representation, you generate words to output your final sequence. Now, you can do this with audio, and a lot of modern methods adopt this method, but for our case, we are not going to do this one. We're going to do a different method, which is a pure self-attention based method. Basically, instead of training two transformers, you train a single encoder model. You input the audio sequence into the transformer, and in the output you generate the text. The third consideration is if you're using a pre-trained model or you're training from scratch. Well, in this video, because we are just learning how to build this, we are going to train it from scratch. But in my next video, or in one of my next videos, I'm going to show some of these other methods, like how an encoder-decoder method is going to look like, and how pre-training on some different task first, and then transfer learning from that task into a transcription model, how that works. So that's for a different video, but for today, we're going to stick with this. So what's the plan? How are we going to convert the audio into the text? Well, the most obvious challenge is that it has 82,637 values. That is a lot, especially because we are going to go for a transformer based approach. That is a lot of values because attention scales quadratically with the sequence length. So we have to find a way to compress this signal temporally, meaning along the time axis, we have to compress it. And to do that, we are going to use convolution. The power of convolution is that it can aggregate local features. Now, if you remember our waveform, you can almost see that a lot of values that appear close to each other, they are quite similar. Like if I just show you this graph again, now this pattern probably occurs a lot in the signal. Like some sort of a feature extraction pipeline that identifies where features are differing, and along with that downsample the audio from this very large sequence into a much smaller sequence. So how are we going to do that? Well, as I've already said, convolution. We're going to use convolutional blocks to downsample the audio signal from this very long sequence into a smaller, dense representation. After this process is done, we would find embedding vectors across the time sequence. Basically, each embedding vector captures some local portion of the original audio, and we have this new sequence of high dimensional vectors, which is a much shorter sequence than the original audio waveform. Then we are going to pass these audio waveforms through a simple self-attention model. What does the self-attention model do? Well, you see, the original audio waveform, when it's calculated, it is very local in nature. It doesn't have access to the entire breadth of the audio. What attention does is it marries all of these different segments together to form compact representations across the entire audio signal. Thirdly, we are also going to use something called a vector quantizer, or more specifically, a residual vector quantizer. So, what is a vector quantizer? Well, what vector quantization does is, given an input embedding, it quantizes it or truncates it into some known sets of values. And lastly, you're going to have a simple linear layer that predicts from this final vector quantized space to one of the characters in our vocabulary. And that is pretty much it. That's what a forward pass through the model is going to look like. And I'm going to show how to code all of this, but I hope you understand what the bigger sort of vision is. Also, if this video helped you in understanding any of this, please do hit the like button, because that helps me a lot in growing this channel and making more videos like this. All codes, slides, and everything that was present in this video and all other videos on my channel are shared regularly on our Patreon page. And as usual, a big shout out to all of the people who have supported our Patreon this month. Thank you. Let's get back to the video. All right, so let's jump into the convolution code. The convolution code has something called as the residual downsample block, which is a simple class that I wrote, which contains a couple of convolution 1D layers. What this does is it basically passes the input waveform through a couple of these convolutional blocks, and it also has a batch norm layer, which helps with something called as an internal covariate shift when you're training long neural networks. Basically, when you're training really long convolutional neural networks, because the previous layers in the network are always updating their weights, the latter layers in the network see new distributions of inputs at every time. So it becomes difficult for the latter layers of network to properly train, because the input keeps changing because the earlier layers keep updating their weights. So batch norm kind of addresses this by fixing the output distribution of its layer to a Gaussian or a unit Gaussian distribution. And I have a whole video on the history of convnets, and in that video I do describe all of this in much greater depth. Coming back, the important thing is the second convolution layer. The second convolution layer has a stride attached to it. What the stride does is, basically, when you're doing the convolution, it slides the convolution kernel by the amount specified by the stride. What this does is that instead of calculating the convolution at each step of the input, it actually computes at a specific interval. And what that does is that the output is now of a smaller size. In fact, the size of the output is going to be reduced by a factor of the stride. Let's kind of quickly check how this layer works. Let's say the batch size is 4. The number of channels is, let's say, a 32. The number of channels basically mean the number of values you're going to use to represent that local point in the signal. And let's say that your sequence length was 100. And so if you do that, you can see that the output of this convolution layer is of shape 4, 10, 49. Well, what is 4? 4 is the batch size. It's the number of examples that we sent. 10 is the output embedding size that we had set. We had said that the input embedding size is going to be 32. The output was going to be 10. The output is indeed 10. And finally, what is 49? Well, you see, the input sequence length was 100, but now it has gotten downsampled, downsized to just 49. Obviously, if you had stride equal to 1, you'll see that the input did not get downsampled by that factor. By specifying the stride, you can say how much to downsample or downsize the input waveform by. If I go back to the downsampling.py file, you have this convolution layer. And so if you look at the forward function, which basically says how the input is going to be processed, this X thing, as we have talked, is going to be the batch size, comma, the input channels, comma, the sequence length, and it's going to pass this through the convolution 1. Then it's going to do the batch normalization, and then here you do something called as a residual connection. Well, what this does, it basically adds a shortcut from your input to the output of the first convolution layer. So residual connections also help gradient flow in long networks, because you add these shortcut paths through which the gradients can flow from your output back to your input. Lastly, you apply the convolution layer again to downsample the waveform, because again the stride is only in the second conv layer. The first conv layer does not have any strides. So that's basically how the residual downsample block works. The second class in this function is just a downsampling network, which, well, it doesn't do much. It inputs a bunch of things like the embedding dimensions and all that, and the stride length. And what that basically does is we create a list of layers, basically a sequence of layers, a series of layers of these residual downsampling blocks, and we pass in the strides, each of the strides into those blocks. So if you pass, let's say 3, 4, 5, it basically means that you're instantiating 3 convolutional or residual downsampling block that's going to downsampling by 3, 4, and 5 respectively. And finally, you have the last convolution layer, which just maps the output into the desired target embedding size. First, we start with the mean pooling, then it loops through all of the layers and downsamples using those strided convolutional blocks or the residual blocks. Then you transpose it and return. Now, if you wanted to see how the shapes look like, let's sort of add some print statements here. Layer, maybe layer I, and let's say I enumerate, and then say final conv shape, and then final transpose shape. And then let's pass in, this is the batch size. The batch size is 2. The sequence length is that. Your input embedding dimension is equal to 1. And let's say that the output embedding dim that I want maybe is 32, and let's say the strides I want to try is 2, 2, 2, 4, 8. So in the first iteration, you downsample by 2, then by 4, then by 8 times, and I also want to set the initial mean pooling to 2. So in the beginning of all this, you also downsample by 2 using mean pooling. And so if I pass all of that in, and let's say the hidden dimension is, let's say, 16, you pass all of that in, initialize a random tensor. So let's see what that runs like. All right, so you can see how it starts. So your shape is that, as you had mentioned, right? here. Then it passed through the mean pooling layer where it downsamples by a factor of 2. You can see that this has been a factor of 2. Now the convolution layer starts with this input, not that. The first convolution layer, it returns something of shape that, where it has downsampled again by a factor of 2. So 118840 becomes 59417. And because you had set the hidden dimension to 16, it had changed from 1 to 16. In the next one, we tried 4, and so 118840 was first changed to 59417, but this gets downsampled 4 times, so now it's 14,853. Then the next one downsamples by 8, so this is 1856. And finally, the last convolution layer, it just increases the channel size from 16 to 32. So your final embedding is 2,32,1856. Finally, you do this transpose operation, which converts from batch size, embedding, sequence length to batch size, sequence length, embedding, because that is the format we are going to pass it to the next module, the transformer. So the convolution model was great for both downsampling the input audio, but also to extract features from the audio that we can pass it to the transformers to process further. The convolution were just local operations, process the entire speech file. But with transformers, we are going to teach the model to learn interdependencies between the signal. Specifically, we will have a sequence length. Let's say the strides are a little bit higher, let's say 6,6,6. Why not? Yeah, 549. Let's say we have a sequence length of 549 with 32 dimensional embeddings, and we want to generate the text. So to do that, we are employing a self-attention block. Now I already have a video that goes through this file where I kind of explain attention and self-attention and transformers from scratch. So I'm not going to repeat everything here, but I'm just going to give a high overview of what each function does. But if you want to learn more about how attention works and how to code it from scratch, I already have a video. Please go check that. All right. So at the heart of this file is this calculate attention function, which basically takes the keys, the queries, and the values, and then computes attention scores and context vectors. Now, the main intuition you need to understand about self-attention is that given those embedding vectors that we calculated in the previous convolution block, we are going to use attention to basically marry them with each other, basically contextualize them with every other embedding in the sequence. To do this, we will first map all of those embeddings into key, query, and value embeddings, and then use something called as the scaled dot product attention to compute how much importance each of these embeddings should provide to all of the other embeddings in the sequence. The result of all of this is going to be a new set of embeddings for each of the original audio frames, where they are a little more contextualized, meaning they have information from across the entire signal. So that basic thing is what this calculate attention does. It just takes the keys, the values, and the queries, and then computes the attention and the attention scores. Then you have the self-attention layer, which converts the input embeddings into key, query, and value vectors, and then calculates the attention. Lastly, you have the sinusoidal positional encoding, which is basically a fancy way of attaching the position information to every audio sequence. And finally, you have the transformer block, which basically aggregates all of this together. It calls the attention layer. It does something called as a layer normalization, which is again one of those internal covariate shift issues that it solves. It passes through another feed forward layer, and then it does another residual connection and outputs it back. The transformer model, this is the final thing that sort of orchestrates everything else in this file, which basically has the positional encoding, and it has the transformer blocks, which is just a list of that whoops, it's a list of those transformer blocks that I just showed, which contains the attention layer, the layer normalization, the feed forward, and all that. And in the forward function, it just attaches the positional information into the input, just a sequence of audio embeddings, and they attach positional information to it and then passes them through each of the transformer blocks in a loop. All right, so the final building block of our architecture is that vector quantizer, right? Now, in my last video, I've already explained what vector quantizers are and RVQs are. So I'm just going to play that portion of the video here so that you are all caught up to speed if you hadn't checked that previous video. But if you already know what vector quantizers and RVQs are, you can skip this next section. So imagine you have a continuous vector of size 512 and you want to convert it into a categorical token. The idea behind vector quantization is simple. You train a code book, which is a collection of, let's say, 1000 random vector codes, all of size 512. Even though each of these codes are continuous, there are still a finite quantity of them, 1000 in our examples, meaning that we have effectively created a fixed vocabulary of allowed speech tokens to represent each audio frame. Then, given the input vector, we will map it to the closest vector in our codebook, kind of like snapping to a point in its nearest cluster center. Once you've got this idea locked in, moving to residual vector quantization is just a natural next step. Let's talk about that in the next section. So the problem with simple vector quantization is that the loss of information may be too high because we are essentially mapping each vector to their cluster centroid. The snap is almost never going to be perfect, so there's always an error between the original embedding and its nearest code vector. The big idea of residual vector quantization is that it doesn't just stop at having one codebook. Instead, it tries to use multiple codebook to represent the input vector. First, you quantize the original vector using the first codebook, as usual. Then you subtract that centroid from your original vector. This error you're left with is the residual that wasn't captured in the first quantization. Now take this residual and quantize it again using a second codebook full of brand new code vectors. Again, by snapping it to the nearest centroid of the second codebook. Then subtract that too and you get an even smaller residual. Quantize again with the third codebook. You can keep doing this for as many codebooks as you want, and each step will hierarchically capture a little more detail that was missed in the previous round. If you repeat this for, let's say, n code books, you get a collection of n discrete tokens from each stage of the quantization to represent this one audio frame. Well, the vector quantizer is as follows. First, you create an embedding layer, and that is just a fancy way of saying you initialize a matrix of random vectors. So if you go back to our notebook and we did this embedding equal to nn dot embedding, let's say the number of embeddings we want to the number of embeddings we want to initialize is 10 and the embedding dimension is 32, and that's the same as the output embedding size of our transformers. So if we did that, we have now created this weight. And so if we did this, this is basically all of the tensors that has been created. It's of shape 10 comma 32. It is basically 10 embeddings of size 32. So here we are just showing the first 5 values of every embedding, and as you can see, this is just a plain old lookup table. So for example, if you say embedding and you pass in the torch.tensor 0 0, let's say, you basically get the zeroth vector, which is this vector 0.37 minus 0.67 1.15. And if you pass in like a sequence of these numbers, so 0 2 3, you get 3 of these embeddings. So this first one is this one, then the next one is number 2, which is this one, this minus 0.12 0.86. this one, and the last one 3 is this one, minus 0.41, minus 0.41. So basically the embedding layer just does that. It inputs the indices and it outputs the embedding vector for those indices. After we have the embedding layer set up, let's see how we quantize the input vector. So we have an input vector which is of shape b comma t comma d. Well, let's, for our understanding's sake, let's say b is just one example in the batch, t is also one, just one single thing, and d is 32. And let's say we create a random number. Now the first goal is to find which of these vectors is closest to our input vector. And to do this, we are going to use the Euclidean distance between this vector with all of these vectors. So let's calculate the Euclidean distance. To do that, the code is this: distance is equal to torch.cdist. Well, let's run this. Let's actually reshape the weight to b times t comma d. And if we run that and we did this, so you basically have 10 new values. Now these values say what is the distance between this input vector and all of these embeddings. So as you can see, this 7.9170 is the nearest embedding. Now this number will obviously be a lot smaller if the embeddings were even closer to the input tensor. Let's create some hypothetical example. Let's say that x is basically embedding dot weight 2. Let's say it's very close to the second embedding, so we are artificially creating this new vector. And let's say we scale the noise down a bit so that it's not exactly same but almost the same. And then if you did see this now, you can see that for the second embedding, so 0 1 2, for index 2, this has a very low distance. So after we find this distance, the next goal is to find the index of the distance, and that is pretty easy to do. You use something called as torch.argmin, and this gives us 2, which is the index of embedding that is closest to our input vector. The last thing we need to do is to return this quantized embedding. To do that, let's just say embedding and this thing. So we want whatever the argmin is, and this returns us this quantized embedding, which is obviously this guy. So all that happened was we got inputted this input vector x, and we did some Euclidean distance computation and some nearest neighbor search, and we returned the nearest vector in our codebook. That is all this function does. You receive the 3D input matrix of shape, batch size, sequence length, embedding length. You do reshape of that. You calculate the distances. You calculate the indices. Then you quantize it by passing encoding indices through the embedding layer. And finally, you also reshape it back to the batch sequence length, and embedding dimension shape. Finally, to do vector quantization, you also have to update the embedding weights as you train the model, because this lookup table starts randomly, right? But you ideally want, as the network is training, to adjust these vectors to move closer to where the input is. And you also want your input to move closer to where the codebook embeddings are. So you basically want your nearest neighbor search to always work. And for that, we do some loss functions where we reduce the Euclidean between the quantized vector and the input. Basically, we want to reduce this value. So the lower we get this value, this 0.4078, it means that the input embedding was that much closer to the nearest codebook embedding. So these two values do just that. They move the x closer to the quantized and the quantized closer to the x. The detach function in Pytorch is a special function that basically removes all of the gradients from a given tensor. So when we do quantize.detach minus x, we're basically saying for this loss, this part of the loss, e underscore latent underscore loss, change everything about X. So when we say that change X, it basically means update all of the weights in the previous layers, like the convolution layer and the transformer layer. Make updates to those weights of those layers, so that the X that comes out of it and into this vector quantizer is very close to the quantize that I'm sending you back, like the nearest codebook vector. And similarly, the Q latent loss does the reverse. It says that okay, the X is constant. I don't want to change X at all. I just want to change quantized. So I just want to change this embedding layer. I want to update this embedding layer so that the values are closer to where my X is supposed to be. And then the total loss is just this Q loss plus some factor and the E loss. And then later on, when we are actually training the model, you're going to see how this loss is also optimized alongside the other losses in the model. The last interesting thing is this thing called the straight through estimator, which is quantized equal to X plus quantize minus X dot detach. What does this mean? Well, let's get one thing straight. The output of the forward function of the vector quantizer has to be the quantized embedding, right? You could have just said return quantized. Why do you have to do this jazz? Well, if you look closely, this is equal to quantized. Like you're adding X and then you're subtracting X. So all that remains is quantized. So what are you exactly achieving by this dot detach stuff? So here's the biggest catch of this vector quantization implementation. You see this torch dot argmin operation. The torch.argmin just finds the minimum index from the vector of the distances, right? Well, this is a non-differentiable operation, meaning gradients cannot flow back from the output through this torch.argmin operation. So essentially, if you did not do something like this and you just return quantized, your output is not going to have any gradient back to X, because you have a gradient stoppage in between by this argmin operation. So instead, what we do is that we do this quantize minus X dot detach, and what this does is that it detaches the quantized embedding altogether, and it just as if the quantization did not even happen and X had passed through as usual. So when flowing the gradients back, it's going to skip the entire quantization step and go from the final layer all the way to the transformer layer, which was before the vector quantization. So to recap, the straight through estimator pretends that while back propagation, the vector quantization layer does not even exist. It just passes the gradients straight back to the input. But we do have these additional auxiliary loss functions that pushes the embeddings closer to the codebook entries and the codebook entries closer to the embeddings. And finally, we have the residual vector quantizer, which is a pretty simple class to implement, if I may say so myself. You just initialize a bunch of these code books, which are basically those vector quantizers, and then given the input X, you loop through your code books, you find the output and the loss for each code book, you subtract the output to find the residual, and then you pass this residual back to the next code book, and along the way you keep adding all of the quantized information one after the other. So the final embedding is just going to be the quantized vector of codebook 0 plus the quantized vector of codebook 1 plus the quantized vector of codebook 2, and so on. And you also accumulate all of the losses of those quantized embeddings to finally give us the total loss. All right, so we've talked about all of the things that we needed to talk about. Now let's put it all together into a single neural network. To do this, I wrote this another file called the transcribe.py file. Let's have a look at what it does. Well, it contains the transcribe model. It has those networks that we have spoken about. First, it has the downsampling network, which takes in the embedding dimensions and the strides and basically downsamples the signal. And then it has the transformer, which again inputs the embedding dimensions and the number of transformer layers. And then it has the residual vector quantizer, which we just spoke about. And finally, it has a simple linear layer, which takes the output of the residual vector quantizer and just maps it to our vocab size, which was what, like, which is basically these values. The final layer of the transcribe model just trains a simple linear layer that maps to the log probabilities for each of those characters. And the forward function is pretty simple. You run the downsampling layer, you run the transformer, you run the RVQ, you run the final output layer, and you ensure that it's in the correct log softmax format, and that's it. That's the transcribe model, just running everything in a sequence. So here we are passing an input audio with batch size 4 and 2, 3, 7, 6, 8. Let's add a 0, why not? Float values, and we have these strides. So let's see how that looks like. So the final. All right, so as you can see, you have the x, which was this, and then it did the mean pooling stuff and passed it through all of the layers to do the striding stuff. And so the final shape was 4, 151, 64. Well, our vocab size is actually 30, so it outputs um, a shape of 4, 151, which is the sequence length after all of this stuff we did with the convolution downsampling, and 30, which is basically the vocab size. So you can imagine this basically means what is the log probability for each batch item and each sequence position. Cool. So the final thing we're going to do is look at the train.py file, which is basically the main training pipeline that we have. Well, as usual, we create the tokenizer, we find what the blank token was. It's going to be important a little bit later. We create our transcribe model. Let's say the embedding dimension is also 32. We get 2 transformer layers. Max sequence length is 400. Yeah, we basically create all of that. Then we get our data set, and then we loop through our data set. The epochs basically say the number of times you loop over your entire data set, and then inside that you loop over each of the batch. So anyway, you have the audio which you extract from the batch, and then here you pass the audio through the model to get the output and the VQ loss. And here you do something called as a CTC loss, which I alluded to in the past, and we're going to talk what the CTC loss does in just a second. But yeah, you do the CTC loss to basically optimize the model, similar to the target, which is the actual target tokens. And finally, your final loss is the CTC loss plus the vector quantization loss after it is scaled by some factor. At the start of the training, I start with a high sort of weight for the vector quantizers because they start very randomly, so they're not going to be particularly useful in the beginning. So you start with a high weight for them so that they come closer to the input distribution faster. But as training goes on, you sort of want to anneal the weight a little bit, and I have it 2.5 after 1000 iterations of training have passed. I'm just linearly interpolating between 10 and 0.5. So that's what this logic does. And then you finally do that weighted sum of the CTC loss and the VQ loss. And finally you do the loss.backward, which computes all of the gradients. And finally you do the optimizer.step, which basically invokes the backpropagation step of actually updating each of the trainable parameters according to the loss. Finally, what is the CTC loss? So CTC, or Connectionist Connectionist-Temporal classification is a loss function designed for sequence tasks where the input and the output lengths do not match, like audio transcription. It allows the model to learn alignments between input frames and output characters without needing the frame level labels that matches every input frame to every output character. CTC basically does this by introducing a special blank token and considers all possible ways the target text could align with the input sequence, including insertions of blanks and repeated characters and so on. During training, it does this kind of a dynamic programming approach to compute all of the probabilities and then sum those probabilities for all of the valid alignments. And basically, this is used as the final loss function which we use to train the model. Again, if we had the data in an aligned format where we knew the exact character or blank token to predict for each audio frame, we could just employ a simple cross entropy loss. But the fact is, we don't. And that's why we use the CTC loss to demonstrate how the model trains. I'm just going to create a new experiment and train on a very small subset of the data. Let's say our batch size is 64. We have a learning rate, and let's say we just train on let's say 100 examples. Okay, here we just want to overfit 100 examples. Now ideally you'd want to train on a lot more data and also use a evaluation or a validation set to see how good your model actually is. But for this video, I just want to overfit this model just to see if the model is learning what I want it to learn. So let's see, let's clear the screen. Python speech to text train.py. Let's see. Well, okay, so the first answer has come, but you can already see that the model is already learning a bit. Now, an important thing about these models are that they don't really utilize any language information. Like, they don't use any text information, like knowing what previous nodes in the final layer have predicted. For that, we need the encoder-decoder architecture that I spoke about earlier. An additional thing about these sort of self-attention model is that because you are sort of utilizing the entire audio at the same time with self-attention to predict each of these tokens, this also means that if the audio sequence is very large, it could get cumbersome. So encoder methods like these are only feasible for smaller chunks of audio, or if you cut down a larger audio into smaller chunks and then transcribe them individually. Alright, so as you can see, the model is training, the model learns stuff, and that's what we want. We want our models to learn stuff. Maybe in a future video, we're going to look at more ways to improve these models. So until then, take care. You're magnificent.